Unit 4 Chemistry, Chapter 11, Part 2, Substitution and Addition Reactions. So, substitution reactions first of all. This happens with alkanes. Now, an alkane, remember, is saturated, means there's no carbon-to-carbon double bonds. So if we want to put anything on it, we have to replace a hydrogen atom with something else. Okay? They are non-polar and they're stable, so they're not too keen on doing that. But if we can put something reactive with them, for instance chlorine gas, okay, and we give them a source of energy, like heat or UV light, then we can encourage them to do it. Okay? We're going to make two products. We're going to make your haloalkane, and you're going to make the other hydrogen that we've just removed attached to, we give it a symbol X. We use X for any halogen. So it might be HCl, it might be HF. Okay? The halogen could substitute into any of the positions on your alkane, or more than one. Okay? And we're going to get a mixture, and we can separate them by a process called fractional distillation. You can look into it a bit more if you're really interested. So for instance, if we had methane and we added chlorine, we can, and use the presence of light, we can take off one of those hydrogens and replace it with the chlorine to make chloromethane. We could do the same thing here. Okay, we've got 2,2-dimethylpropane. Okay, we can substitute one of those hydrogens, or it could be more than them, with the chloro group. Okay, and here we're making our HX. Yeah, and generically, more specifically here it's HCl. You'll notice up here they haven't shown the HCl that's made. It is made. Organic chemists are quite sort of self-centered in that all they really care about is the organic compound that's made. If you're doing a full balanced equation, of course you're going to show the HCl. If you're drawing it with structural formula, then just this is fine. And in fact, what you'll also see is quite often the Cl2 would also be on the arrow. Alkenes won't do a substitution reaction because they've got a double bond. So we can add to them. And because we're adding, we call it an addition reaction. So we take that carbon-carbon double bond and we break the bond, just the one part of it. Okay? So we leave a single carbon-carbon bond there, and we add something else in at each carbon. What we're normally adding in, we might be adding something like HCl. Okay? Or we could be adding something like Cl2. Depends what we're replacing it with, what we need. We could also add an alkene to itself, again and again and again over. And that's going to make a polymer. Okay? That polymerization will normally require a catalyst, which is normally a metal. Okay? So we could take something like ethene and add bromine, and we're going to make 1,2-dibromoethane. We could also add hydrobromine here, hydrogen bromide, okay, or hydrobromic acid, in which case we'd add a bromine to one side and a hydrogen to the other. Okay. The other thing we could add here is water. If we added water, we'd get an alkanol. So we'd add OH to one side and hydrogen to the other. If we were going to do that, we would also need heat, and we would also need a phosphoric acid catalyst. H3PO4 would need to be added as a catalyst. Okay. Here are some examples of these addition reactions, and you can see they're much more varied than the reactions we were looking at previously. Okay. So we can add OH groups to make a diol. We can polymerize it. We could add something like Br2 or Cl2 and make a dihaloalkane. We can add hydrogen, turn it back into an alkane. There's really no reason why we would do that, but you could. Okay. We can add some water to make an alkanol, and here's what I'm saying, you add the OH to one side and a hydrogen to the other. Or we could add a hydroalkane. Okay, so we could add something like hydrobromic or hydrochloric acid, and here you'd add a bromine to one side and a hydrogen to the other. Okay. Addition reactions, much bigger variety because this carbon double bond is a much more reactive site, so we can do a lot more with it.